All right, so here we're going to do a hypothesis test and a confidence interval simultaneously for one population mean, just so you can get the gist regarding this particular lab. Follow what I'm doing to a T. So the statistical question for a hypothesis test would be, is the population mean amount of calories in all fast food items equal to 450.25? Okay, again, we're doing a convenience sample, so we know for a fact there's going to be some biases in terms of our results, but we can still talk about it. And so, in terms of stating the null and alternative hypothesis using words, it would look something like this. Um, the population mean of calories in fast food on the fast food menu is equal to 450.25, and then the population mean of calories in the fast food, I should say on fast food menu, is not equal to 0. Or equal not equal to 450.25. Okay. Whereas if I was dealing with a confidence interval, it would be the following question. It's stated a little differently. Okay. The following question would be, what is the population mean of calories in on the fast food menu? And ideally, adding items would be ideal there. Okay. And so one of the ways that we can summarize this information, one of the ways we can actually get, the mean and standard deviation, the sample size, and I'll argue this is a little bit of the easier way to do this, um, is using this functionality called summarize, because this is actually coming from this package, StatCalPoly package. Summarize one quant variable. Data frame is MCDF. That's not correct. It should be McDonald's data. Sorry, so copy and paste this. And then run this, okay? And then it will give us our because it should be lowercase c. Sorry about that. Cut that real fast. That's good. All right, so it tells us the number, the sample size, the mean is 368.27. Standard deviation is 240.27, min and max, okay? However, a little bit more, and again, you can ignore this x1 here. A little bit more of a complicated, not to say complicated, but one of the ways that could be used to get the same exact result using the tidyverse function, or at least functionality, is, again, this should be McDonald's data frame, or data, MCD, okay? And then we use calories, lowercase c, lowercase c, lowercase c. Again, there's many ways to the top of the mountain, choose one, many ways to the top of the mountain, no many. So this is going to give us the same answer, but and using different functionalities. So it's saying using the mean function, standard deviation function, min function, max function, whereas in the backhand, this is doing all that hard work for us. We don't have to specify the mean, standard deviation, so on. Okay, this is a little bit more robust. This is, you can do more things with this functionality. Okay, and so there's our information. So visualizing this information, we would use the following functionality. Okay, create a new R chunk to visualize, and therefore I can also say up here, summarize, okay. And the reason why I put hashtags in front of here, what these allow me to do is to make the text bigger when I compile it. You see what I mean by compile it in a moment. Here, I'm just going to paste this here. Okay, this shouldn't work because this should be McDonald's data, and it should be lowercase c. And for some reason, this blue, that's interesting. This is going to create a histogram of our data, okay, which is cool. So in your back of your mind, what is this shape of, what can be seen here? What's the shape of this visualization, okay, of this histogram? Ideally, you should say skewed right because we have outliers to our right, okay, and it's unimodal. It's unimodal. It's right there, just one hump, okay, that's good. Okay, so in terms of our analysis, the assumptions that we at least need to talk about, there's two. The data needs to be random. Okay, the data needs to be random, and each observation needs to be independent. We don't. The data, first of all, is not random. Each observation, each menu item is definitely not independent. Because there's, like, let's say for example, there's something wrong with the sausage. Sausage is being produced. That messes up all these items. There's a dependence between the observations. And mind you, I didn't say this in the first video. This is real data. This is real data. I'm actually really excited talking about this. All right. So then, doing the analysis by hand, we actually will get this is the equation. Since we're doing a hypothesis test, this is the equation for the hypothesis test. Or this is the test statistic to calculate it. Okay, it should show up. I don't know why it's not showing up automatically. Let me press into that a little bit. See what happens. Okay. Once this, okay, so I'll let it take its time. So at the end of the day, if I wanted to calculate this by hand, we need to look at the actual output first. Okay, so what I'm going to do is copy and paste this into here, into the console, so I can see the numbers on the right. Okay, and so in terms of the equation, we know our test statistics should be equal to the mean, sample mean 3. I'm gonna copy and paste because of time. I'd have to work. So it's 368.27. That's the sample mean X bar. Our hypothesized value 450.25. That's mu. Our standard deviation 240.2699. That's our standard deviation, and 260, which is our sample size. And so what's crazy here is the parentheses. Be careful. Be careful. Be careful. Okay. Be careful. And so we do that for our test statistic, and then we press TS down here. We actually can now run this. We run this chunk, we see what that value is. Negative 5.5. Okay, based on our lesson in class, remember that's beyond 3.5 and 3.5. We know for a fact we should have a small p-value. Okay, so that's what we would do for our test statistic. From there, what I would do is show you all the process to finding the confidence interval. Okay, and I'm just going to copy and paste it and explain it, what's going on here. Okay, so here my point estimate PE is 368.27. My critical value, this is how I'm finding my critical value. And I'm always going to either give you the code, or I'm going to have you do it yourself. Okay, and so based on what we know about alpha, you know, if it's a 95% confidence interval, we take 0.05, right? We divide it by 2, and our degrees of freedom is going to be n-1. Okay, so that's what's happening here. 0.025 is our alpha divided by 2, and 260 minus 1 is our degrees of freedom. And so when I run this, I'm able to get, okay, my CV, and I'm showing you different ways of doing the same exact thing, just so that you can, you know, see that the 1.96, and my standard error is 14.9. Okay, and so when I run this, run all this, okay, I'm going to get my lower bound, upper bound. Okay, 338.9276, 397.612. I know we didn't finish conclusion regarding the hypothesis test, but we'll see. You'll see why in a moment. All right. And so we have a hypothesis test in terms of the math. We have our confidence interval in terms of the math. And then what we could do, okay, or what we're going to do is have R actually run it for us. So we do t.test, right? And then we use McDonald's data, comma, and we're going to say mu is equal to, let's say McDonald's data, and we're going to do a dollar sign. My apologies. I want to make sure I do the right thing. Calories. Mu is equal to that, our specified guess, 450.25. Okay, so then when we run this, okay, it's going to automatically give us our test statistic. Okay, negative 5.0517. The reason why theirs is negative is because they reversed it. They flipped this. And our result to our null hypothesis is going to be the same thing. We're going to reject the null hypothesis regardless. And it also gives us a p-value. Okay. They calculated degrees of freedom in a tad bit different way, but we're not going to emphasize that here in this class. Oh, no, we did it the same way. 260 minus 1. That's right. Then we have a 95% confidence interval as well. Okay, which is what we got here, 338.927 and 397.61. Okay, and that's the mean. So that's pretty much it for one population means. Hopefully this video was informative. Thank you for your time. You're greatly appreciated.